Okay, so so Umut is a good friend of mine from very earlier years. So we met like almost 20 years ago, and he is now an associate professor at Carnegie Mellon University. And his research interests are in formal methods, programming languages, concurrency, parallelism, quantum computing, and AI and machine learning. He has numerous best paper awards. At Popul, QCE, and ICFB, and so on, and it goes. And he's very proliferate, so he has 2 books, and now he's going to tell us about bridging safety and performance.
Everybody, delighted to be here to talk about this work on bridging and safety and performance. As people are interested in declarative languages, I hope that you will appreciate the goal of this work is to bridge really good things about declarative languages and really good things about imperative languages, bring them together. So bringing safety and performance, really, as the title says. And this work has been going on for a while. The talk here covers about, let's see, 2016, so it's like about 8 years of work. A lot of people have contributed to this, probably dozens of papers, and some people have made major contributions, include my students, my research group at Carnegie Mellon, and other collaborators at other institutions, including Stanford and Northwestern. And so without their contributions, this work really wouldn't have been possible. So to put this work into some historical perspective, in computer science, as computer scientists, we somehow accepted this dichotomy between imperative languages and declarative languages. If you want to write fast code that, quote unquote, matters, we go and use imperative languages such as C, C++, maybe even Java. And you know, the goal is to get good efficiency, good performance, because that's what matters. Now, if we want to play around with good ideas, we use declarative languages, functional languages, included in declarative languages. And our goal is really to write beautiful code, to have safe code. Safety is very important. But we know that we're going to get bad performance. Okay, and we accept that somehow. If we use imperative languages, we get performance. We do not get safety. If we use declarative languages, we get safety, but we do not get performance, and we are somehow happy with that. Well, I think this is unacceptable. And I think time is showing that it is unacceptable, right? Our systems are getting hacked. A lot of things are going very bad because of poor codes, unsafe codes. Yet, we continue, in some sense, living with this dichotomy. Okay, so why can't we just bridge this gap? Why can't we have both safety and performance at the same time? Well, I believe, of course, we can. And there are ways of doing this. I can think of 3 ways. One of them is improve the performance of declarative languages. Another way is to improve the safety of imperative languages. And the third way would be actually to include the capabilities of both so that we can express more and more things declaratively in some sense and let the language handle a lot of the low-level tasks. So the second option here, improving safety of imperative languages, in some sense is already going on. There's a big effort in the development of Rust language. So I won't talk about that. What my interests are more about improving the performance of declarative languages and their capabilities. So points 1 and 3 is what this talk will be about. So from this perspective, we've been doing a ton of work in 3 different areas. One area is basically high-performance parallel functional programming, which may sound like an oxymoron, right? Parallel function programming is horrible in terms of performance. How can you make it have performance? I believe we can. I'll show you how. Responsive parallelism is taking parallelism, conventional parallelism, and actually enhancing it with better, much more interesting performance criteria. And the third angle is starting to actually manage very interesting performance properties within the language itself, within the runtime system, that I call automatic parallelism management. So in this talk, I'm going to talk about these two parts, the high-performance parallel functional programming and automatic parallelism management. Now, before I start, I think everyone pretty much knows, maybe I need not say this, but sequential hardware has gone into the dustbin of history. That's a fact. And almost everything today, ranging from your phones to our laptops to servers that are responding to your LLM queries, they're highly parallel. Parallelism is everything, everywhere, all at once, literally, right, in some sense. Yet, writing parallel codes remains to be challenging. Good performance requires extensive manual optimization, usually in imperative languages. Correctness is very hard because of concurrency bugs. So, natural question is, how can we bridge the gap? Well, it's not a novel idea that functional programming is safe for parallelism. Functional programming is beautiful. It's got clean and powerful syntax. If you add types, you get even more powerful things. It has a formal semantics. And it's parallel by default. You don't even have to think about parallelism when you're writing parallel functional programs because functional programming is parallel. You don't have to even think about it. It's just by default parallel. And it's completely safe, right? But performance is very proved hard to improve. There's been decades of work on this, right? Big effort in the Haskell community. It's proved hard. But it turns out it's doable. So this talk will show you how. But before we get there, let's develop some sense of how functional programming can allow you to write parallel codes in a very safe way. So here's the primitive. Okay, I don't want you to understand necessarily the code here. But this is a primitive that allocates an array and initializes it with a function specified by init. Okay, init is this is a higher order function. It takes a function, it creates an array and initializes it. So this code does memory allocation. It allocates an array, and it actually updates these cells that it allocates, and it can do all of this in parallel. So it can do all of the array fills in parallel up to some log factor noise, so to say. So there's lots of parallelism here. Convincing yourself that this is parallel safe is not too hard. You just have to reason a little bit about the fact that you're not writing into the same location multiple times. But it's not too hard. And the par primitive there is the only primitive that you need for parallelism. So you only need a single primitive for parallelism, that's all. Okay? Now, once you have that primitive in your pocket, you can go ahead and write more and more complex things. You can map over an array a function, okay? And you can implement that by just these 4 lines of code. Okay, you just call tabulate, basically, that's it. Now, what's amazing about this code is that not only it's highly parallel, but it has absolutely no effects here. Okay, this is a purely functional code. Not a single effect. Now, not a single use of par either. Okay, it's parallel by default. Here is reduce. Okay, so it's a reduction. That's going by map and reduce. That's how you would write reduce in an ML-like language. Lots of parallelism. This is parallel safe. Absolutely no effects. Single primitive par suffices. So you can go on and write primitives like this over sequences. Okay, so it's really relatively easy. Once you have all that, you can start writing more interesting codes. You can do token counting by mapping and reducing. 3 lines of code. This is parallel. It's safe. Not a single mention of parallelism, but it's highly parallel. Now, you can say those are trivial things. How about more interesting things like graphs? Well, here's a parallel breadth first search. You can actually run this code. Okay, this is all that there is to parallel breadth first search. Now, because it's operating on graphs, it's exposing irregular amounts of parallelism. Note that not a single use of par exists here. Not a single effect exists here. Completely safe for parallelism. So, okay, so lesson is, well, you can, using functional codes, you can write parallel programs, very interesting algorithms, not hard at all. Now, this is actually how we teach at Carnegie Mellon. We teach our undergrads parallel programming using this technique. In their second year, they learn algorithms, parallel algorithms and parallel programming at the same time in their main algorithms and data structures course. They excel at it, okay? It's that easy. Sophomores can do it. But when they run their code, they realize that things are not that easy because they actually end up getting very poor performance. They used to, I should say, which motivated all of this research. So now why? Well, it turns out fundamentally, parallel functional languages have come a long way. So you can improve compilation, you can improve optimization, but the main bottleneck, as pretty much is the case in any parallel thing that you want to do, is memory. There is already very high pressure on memory. Functional languages already exert a high pressure on memory. And when you throw parallelism in there, it gets incredibly worse, right? Because we have parallel tasks allocating at the same time. Now the memory manager must somehow satisfy that, as it also does parallel memory management, parallel garbage collection. Well, this is not a solved problem at all. It turns out parallel memory management, memory management allocation and garbage collection is very, very hard, and essentially an open problem. So this is in contrast to sequential memory management, which is, it's just like, again, very well understood problem, lots of algorithms, lots of different things you can do, but parallel memory management is not well understood at all. So why? Why is that the case? So let's dive a bit deep. So parallel computations have traditionally been modeled by using these DAG structures, where these nodes show or denote tasks that can be executed in parallel, and the edges denote dependencies. Now, you can take a program and map it to this kind of model, and theory people have developed many, many, many interesting algorithms, scheduling algorithms, analysis techniques, bounds, and so on and so forth using this model. Now, I should note that when I say theory, I mean analytical, what I call sometimes Turing theory, complexity theory-based approaches, algorithmic approaches. They have developed all kinds of interesting theories about how to reason about parallel computations. Now, being theoreticians, to them, memory is just another operation, okay? They don't necessarily account for the fact that memory is like 100x slower than your plus operation. And consequently, they largely ignored memory from this model. This fundamental model basically ignores memory, okay, for the most part. Now, in order to solve our problems, to establish this bridge, somehow we need to add memory to this model. How are we going to do that? So let's suppose that with each task, we associate the memory that it allocates. So in some sense, each task owns the memory that it allocates. And we draw these edges for use of allocated memory. For example, if task D uses a memory allocated by A, then we add this edge. So note that we don't distinguish between read and write. Just use is all that matters. Now, in 2020, we proved this theorem that basically said that if you have a deterministic race-free or declarative functional program, then this here has a particular structure. And what's that structure? The structure is that there are no cross edges. All of these edges go either up from a node to its ancestor or down from a node to its descendant. But they never cross. So you don't get these types of edges. You don't have edges between B and C, D and E, never. It turns out this is a result of determinacy, race freedom, or functional programming. Now, we call this property disentanglement. And you might say, whoa, that's such a strange thing. What is that exactly? Okay, why would you call that disentanglement? What's the essence of that? You might ask, like I asked. After some thinking, I realized there's something very fundamental going on here. What is that? What's that? So this DAG essentially is a generalization of a notion of time from a sequential to a parallel program. In a sequential program, everything executes sequentially, so the time is simply a chain. In a parallel program, things can happen simultaneously. So you need a DAG to effectively capture time. To actually represent time, you need a DAG. So disentanglement or this idea of no cross edges. What that's saying is that the use or dependency chains respect time. I only use a piece of memory that's allocated before me. That's it. Okay, so in some sense, it's a very, because it is a very natural thing, and somehow, I guess for a long time we missed it, but it came out as a result of this work. Now, perhaps given that understanding that this is just a generalization of the notion of time for parallel programs, it shouldn't come as a surprise that disentanglement turns out to be very natural and broadly applicable. So these are lots of benchmarks here. All of them are disentangled. Now, note that these are not all purely functional. They're not written all in a purely functional style. But even if they are not written in a purely functional style, if they're written in a purely functional style, they're disentangled. But even if you make various performance tricks and do not get out of the purely functional principle, you still remain disentangled. Okay, so all of these are highly optimized, really sophisticated algorithms, and some of them are really sophisticated algorithms, and they are all disentangled. Some of them include, in fact, atomic read-modify-write operations. They are still disentangled because atomic read-modify-write operations do not actually involve allocation because they operate on machine words or memory words. So it's very interesting. Now, okay, but what's the use for disentanglement? Is it just some intellectual exercise? No. Okay, so recall that our goal is to bridge performance and safety. And we need a tool to do that. We can't just continue doing, like what we've been doing because it proved hard. So we need a new concept. And disentanglement turns out to be this concept. And the idea is that disentanglement effectively says the independencies in computation tell you about the independencies in memory structure. If two computations are independent, D and C are independent because they're on parallel paths. There are no dependencies between them. That's what disentanglement says. It says that if there are independent tasks in a computation, they are actually independent in terms of the memory that they operate on as well. Okay, so that's the essence of what we get from disentanglement. Now, concretely, it turns out we can take disentanglement and turn it into an algorithmic idea to organize the memory into a hierarchy, independent, effectively, regions that mirror the computation DAG. So I'm going to show you how to do that. Suppose we have this computation, and we want to execute it. What we're going to do is we're going to start execution at root, and we allocate a heap, a region of memory. And when A forks B and C, we're going to allocate 2 new regions for them, and so on. Okay, we keep executing like this. Now, when we join, okay, when we join, what we're going to do is we're going to unify all of those heaps on the left. I'm going to show that by simply merging into the parent. So they're effectively the same thing with a little bit of a squint. Okay, so with that squint, what we have here is what is a DAG here corresponds to a tree of heaps. Okay, so very simple structure. And the heaps, these 2 heaps are independent heaps because they belong to independent tasks in the computation. Okay, so on. So now, once you have this model, disentanglement tells you that all pointers in memory point up and down in this heap hierarchy. Okay, that's it. Basically, you have up and down and no cross pointers. Now, a nature of parallel computation is that when leaves are executing, all of the internal nodes are suspended. Okay, so that's an important invariant. And that's important because note that independent tasks can still communicate by accessing a joint heap. So they can still communicate by accessing a joint heap, but that's okay because that heap is effectively suspended. That's very important, it turns out. So based on these 2 observations, we can, as the computation execute, garbage collect heaps that are at the leaves completely independently with absolutely no communication with anybody else. Okay? So basically what the computation told you is that these are independent tasks, and what disentanglement tells you is that, well, because the tasks are independent, their memories are also independent. So you can garbage collect them at any point, whenever you want, with absolutely no synchronization with anybody else. Okay? Now, the internal nodes, it turns out, you can also garbage collect them because they're suspended. Okay, they're a little bit tricky because they have up pointers, so you have to be a little bit careful with roots. But that's okay. It's nothing unknown, okay? Memory management people have developed all sorts of techniques with dealing with things like that. And in terms of parallelism, that's trivial because it's suspended. So I can go and collect the sweep the memory. So it turns out this idea works really well in practice. And we have implemented it, and we saw some really good results. But one of the things that I'm very interested in is not just implementing things that run well in practice, but also understanding why do they do what they do. So consequently, okay, it works in practice, but does it actually work in theory? Okay, can we prove that this is efficient? Well, this turned out to be very difficult. After a few years of work, finally, one of my students actually got the brilliant idea that solved this theorem, Jatin Arora. And in PADL' 2021, we proved that basically, that's a long theorem, I don't want to read that, but effectively, we can memory manage the memory of a disentangled parallel program efficiently. What I mean by efficiency here is very little overhead that we can amortize against the cost of the computation. And we haven't proved this, but it's not hard to prove that this is effectively optimal within a constant factor of the optimal. And the key idea behind the proof, which kind of, again, Jatin came up with, is a very novel idea. The idea is you don't just schedule tasks over your processors, which is what these languages do typically. You also schedule memory by scheduling these heaps. Okay. So yeah, so I highly recommend going reading over that paper if you're interested in this. It's some very good stuff there. Anyway, so it turns out that theorem, over the years, we've extended it from disentanglement to also entanglement, meaning that we can actually allow cross pointers, all sorts of interesting things. It turns out these are very rare, but you can allow it, and you can enhance the theory to account for entanglement as well. So you really, by following this approach, you do not lose anything. Now, the key idea for supporting entanglement is effectively to treat them as special pointers. The cost increases, but because they are so rare, in some sense that's okay. So implementing this took a fair bit of work, and we took the ML language, standard ML language, which doesn't have parallelism. We added parallelism to it with a single construct, the par construct, and otherwise we support the entire full language, including all FX module system. Everything is in there. And after years of work, we basically developed this compiler that we call Maple. That's able to run parallel programs written in this language very, very efficiently. It uses both a task scheduler, as I mentioned, and also a heap scheduler to schedule the heap. Now, I'm going to show you some experimental results. Okay, so how well this does. And then try to convince you that this bridging is actually entirely possible. Now, this plot here shows the speed up of our ML codes with respect to a C and C++ baseline of highly optimized codes. These C++ codes are optimized not by us, but by another group of people actually at MIT at Carnegie Mellon working together. They've been developing these algorithms over two decades now, I believe. And so very, very highly optimized algorithms, very sophisticated algorithms in there. And on 72 cores, Maple delivers 30x speed up over C++ sequential codes. And it's only 2x slower than C and C++, both in the parallel and the sequential case. Okay, so that's the lesson. So note that C codes are actually managing memory manually, so using highly optimized memory allocators. So this comparison is actually really apples and oranges. We're not comparing to a garbage collected language, we're comparing to a manually managed language, and the performance gap is factor 2. Now, really, we should be comparing to not C, but other memory managed languages. So let's do that. Compared to Go, okay, we are 2x faster. Okay, so that's important. C is 2x faster than us. This is normalized with respect to us. Go is 2x slower. Java is 2x slower. OCaml is 6x slower. Okay. I threw the OCaml in there just so that we have another functional language. Now you can say, doesn't that come at the cost of space? Because space is usually, okay, where functional languages pay. What's amazing is that we are actually better in using space than C codes. We are using 20% less space, okay? With respect to Go, we are using, I don't know, like 40% or something less. With respect to Java, we're using, or Java is using 4x more memory than us. OCaml is using about 2.5x more memory. So we are improving both in time and in space. We are improving even over the C code. Okay, so that's incredible. Now, summary of all that work. Okay, that's like, again, I said, 8 years of work there packaged into like a couple of slides. I believe high-performance functional programming is possible. And it's possible to bridge performance and safety. That's not, of course, we need to be clever. Of course, we need to do cool theory. Of course, we need to do cool engineering, but it's possible. And also another thing I've learned over of this work is that it's always possible to improve your results, okay? All these results can be improved. I'm sure if we go back to the C people and say, oh, you know, we're 20% better than you, I'm sure they will be able to improve their results a little bit. And we might be able to improve it back. Really what matters is, in some sense, the methods. And the methods, what I've learned from this work is that you really need both the church theory and the Turing theory. By church theory, I mean formal methods and so on. Some of those theorems I mentioned required really significant formal methods effort to prove. And the Turing theory is really being able to reason about performance. That turns out to be really important because if you can't reason about performance, you can't design these algorithms that actually, runtime systems and algorithms that actually do well. So it's important to bridge not the two, safety and performance, and perhaps not surprisingly, to bridge safety and performance, you need to bridge the two theories of Church and Turing. And of course, experimental validation is very important. Any questions so far? I can take a little break here and handle your questions because the rest of the talk is somewhat independent.
The previous slide where you have the different languages, we looked at Clojure.
No, I have not. Because it has
Very basic, small primitives that handle parallelism, but its concepts or its assumptions are very different than yours. Okay. So the idea in Clojure, as I understand it, is that it assumes local garbage is very fast to collect, so it maximizes local garbage.
In some sense, our allocator does that as well, so it kind of maximizes local garbage collection. Yeah, that turns out to be very important, in fact, for efficiency reasons. Yeah, but yeah, so we should compare to Clojure.
The kind of way you described it is you had the heaps and then you allocated subheaps, and then you could just collect those subheaps. Does this kind of translate at all to something like a compacting collector where it's going to be moving things around because things are...
Yeah, in fact, that's a very good question. Yes, so here it turns out these leaves are trivially compact. You can use whatever collector you want. Actually, you can move. You can, if you want, you can mark and sweep, but you can also move and compact. And the collectors that we use move and compact. That's very important because it's locality and so forth. Yeah.
Think of these this tree as like a conceptual thing, not necessarily how it's laid out in memory. Okay.
So I think I'm abstracting over stuff, a lot of stuff here, and yeah. So the implementation is very, very different from what I've described here. It obliges by it. It respects it, but it's very different. It's much. There are a lot of details. Yeah. Good question. Yeah.
It is very cool stuff, Umut. I have a question. If you go to I found those two lines, mumble speed up over C and then 2x slower than C, a bit confusing. I'm assuming this the slowdown is yes, the sequential. So that means the second bullet implies some parallelized version of C and C++, or am I?
Right, I went through this very fast. So that's a very good question, right? So these performance measurements, we have to be careful about them. So what we did here is, typically you compare a language to itself, because you say, okay, I speed up, this much time compared to my sequential version. What we did here is we compare Maple's parallel version to C sequential. So we're like really very hard on us in some sense, right? We done sequential C codes. Does that make it clear? Oh, so this one here, yeah. So this is the parallel version of our codes are 2x slower than parallel versions of C codes. Yes, yeah.
How does one parallelize the C code in this case? I'm just curious. What sort of library or what we use?
Oh, so this is work by Julian Schur at MIT and Guy Belalak at CMU. They have been like developing basically a library-based parallel C codes. So they're mostly interested in implementation and algorithms. So they develop cool algorithms, implement, et cetera. Yeah. So we're comparing to their work. So that's not. Yes, sir.
So thanks, great work. So I would like to know what is the speed up with respect to the number of processors. So because here you have 72 cores and do not use. So what happens? So if you, because usually so I'm impressed by 72 cores that you can also have such speeds up, but because often you get this for a slow null number of cores, you get a good speed up and then it turns down.
Right, absolutely, you're right. I mean, so these speed ups are incredibly good. So I should say. So obtaining speed ups on 72 cores is not a child's play, because really that's pretty much the max you can obtain because of the hardware constraints. Even if you have 72 cores, typically the max, because of the memory bottlenecks, the max you can obtain is 30 cores. So we're 50%, I think of it as. So max you can obtain is 36. We're getting to 30, very, very close to max possible.
A speed up of 8 if you have 8 cores. Good.
Papers and whatnot, we go to 72 cores, whatever, 144 cores and so on. Any more questions? Yeah.
Functional and imperative programming, you haven't mentioned the fact that many imperative algorithms rely heavily on destructive assignment on arrays. When you're parallelizing functional algorithms, it's usually a pain in the ass how to simulate that. Do you think this is relevant for this discussion? I think that you're using merge sort and not a quick sort or with update in place. Can you elaborate on this?
Not actually, yeah, of course. So I think that to repeat everybody. So in imperative languages, you typically use very different paradigms of programming than in functional languages. In functional languages, you're copying data all over the place because you're not allowed to update them so much. And in imperative languages, you typically update everything in place. So there's a huge difference between the kinds of codes that you write. Now, our codes, it turns out, because of the way that we've abstracted our codes, organized our codes, almost all side effects happen in what we call sequence libraries, array libraries. So the user codes do not typically do any side effects or anything like that, but everything is happening at the level of abstract data types. So we've been able to basically, by using functional programming paradigm, push all of the dirty tricks inside array libraries. So the programmer pretty much writes functional code. And that's how these codes are written. Yeah.
Maybe continue with this. Many of the optimizations done in imperative languages rely on heavy use on cache memory and utilization of that things. How does different hierarchies of memory levels?
Very good question. So this is a research direction. It's well known that, in fact, so I did some work back in 2000, 25 years ago, that showed that you can take these bags and schedule them to improve locality on hardware. We're not doing any of that here. But it turns out, research direction, that's possible, and it would probably be fruitful. But some of it, I should admit, happens naturally, it turns out, because of the way we schedule things and so on. So that is an important factor here.
And maybe also
Yeah.
handling the arrays, that's where the case thing improves.
Yeah, exactly. So I think all of these could be fully automated, right? And we can, in fact, manage locality automatically as well. That's, again, a research direction. Yeah, so very good question. There's a lot to do here. And we can, there's perhaps another, I don't know, 50%, perhaps 2x improvement that we can get by doing things like that here. Yeah, very good question. OK, so thank you all. I'd like to move on, and we can take more questions towards the end. So good. So in the second part of this talk, the question is, can we increase the reach of declarative programming so that the language does more of the really nasty optimizations that we have to do by hand automatically? Okay. So it's a reality that parallel programs require extensive optimization. And an unoptimized parallel program runs at least 10x slower than a sequential one, okay, by default, just like that. And the key optimization that you do is what's known as granularity control. And the idea is to not parallelize small pieces of computation. Very simple to say. But it turns out it's a huge headache, and huge headache to actually deal with this in practice. Let me just give you a simple example. So if you have a par4 primitive that iterates a number of loop iterations in parallel, you can write tabulate like this. This allocates an array and fills the array in parallel. Okay, very simple to write. If you run this code without optimization, you're going to get 100x slower. You're going to be 100x slower than an optimized piece of code. How does an optimized piece of code looks like? It looks like this. You first have to make parallelism explicit so that you can control its grain. The problem here is that it exposes too much parallelism. So if you talk to people, people sometimes say, oh, parallelism is hard. There's not enough of it. No. That's not true. The problem is parallelism is easy. There's usually too much parallelism. The problem is there's too much of it. So you have to spend a ton of time to manage it. That's why you get like this 100x slowdown. So you really need to do things like this, where you say, OK, I'm going to explicitly expose parallelism. And I'm going to put a grain on it that says, if my problem size is small, then revert to a sequential piece of code. OK, that's what this does. Now, look how ugly this is. But it's not only ugly, but it's actually almost impossible. Because what should this grain be? Should it be 10? Should it be 100? Should it be 1,000? Okay, what should it be? Well, there's really no good solution because it depends on what this init does. Init might be a tiny function, set this element to 0, or it might be go compute Fibonacci 20. It could be a giant function. So there is no way to determine that grain, period. Okay? So it's an unsolvable problem because it depends on dynamic dependencies and dynamic data. Now, worse, the init itself could be parallel. What if init is parallel? Then what do? What should the grain be? Well, nobody knows. Okay? So what people do is they just throw random constants in there, hope for the best. Okay? And what happens is you spend hours optimizing, and what you end up getting is a nasty piece of code that's overfit for your hardware. If you try it on a different hardware, of course it doesn't work because the constants are not optimized for that hardware, and so on and so forth. So there ought to be clearly a better way of doing this, but it's not easy. Okay, so how do we do this automatically? Somehow, what we want is write this code and use my daughter's favorite book to pick the right grain. Okay, so that everything works. How do we do that? So it turns out this is possible. I'm going to try to explain the idea with a metaphor. Now, we all need oxygen to live, right? And think of oxygen as parallelism. In a parallel computation, you have to supply parallelism constantly. That's your goal. And in our bodies, we have to supply oxygen to all of our cells. That's our goal. How does our body work? It has a heart. It beats, and it supplies oxygen not continuously, but discretely. Only at the heartbeats, it supplies the oxygen. Okay, so this was the inspiration. Can we do the same? Somehow, parallelism, like the oxygen, we're not going to try to expose it continuously as we traditionally do, but actually do it discretely. Okay, how are we going to do that? Okay, so the idea is what we call heartbeat scheduling. So you take your DAG and you execute sequentially. You're not even worried about the oxygen, okay? But you note the parts where you can create parallelism. You just kind of take a little note of the parts where you can create parallelism. And you have a heartbeat that's beating at every millisecond or so. And when the heart beats, you go and create parallelism, but only when the heart beats. In between the heartbeats, you're doing actual, honest-to-God sequential work. Okay, so that's the essence of the idea. Now, we proved in a PADL' 2018 paper that with some care, you can do this with no loss of efficiency and no loss of parallelism. Okay, so the no here is a little bit of quoted. The actual theorem is quite a bit complicated, but what no means is arbitrarily small. Effectively, it turns out, by speeding up your heart, you can supply as much parallelism as you want, and by slowing it down, you can supply less of it, and so on and so forth. But there's usually a sweet spot, obviously, system setting. Now, this proof is very tricky, very, very tricky. We didn't believe it ourselves because it turns out like this theorem, when you start thinking about it, it's actually very hard because the problem is that if you delay parallelism here, you're delaying all of the parallelism that parallel task is going to spawn. So in some sense, you expect impacts to accumulate. You do not expect to be able to control parallelism. You do not expect no overhead from this approach. Because if my heart doesn't beat here, I'm kind of screwed. Because my oxygens are going to start my cells are going to start suffocating. So my heart needs to beat up faster in order to catch up. But we're not using anything like that here. We have a fixed heartbeat. Okay? So it's actually a very tricky theorem. But it turns out it's possible to prove. And the key idea is that when you're parallelizing, you can't just parallelize every task. You have to parallelize the uppermost, the earliermost task, it turns out. So that delay, the heart, makes sure that the biggest chunk of work gets parallelized. So we proved this thing. And it turns out, even though the idea is very simple, practical realization is it's a nightmare. It's very, very challenging, okay? How do you implement this hard? Do you implement it in the hardware? Do you implement it in the software? It turns out there are all sorts of overheads. So years of effort. So we did it both in actually ML and C, it turns out. And it works incredibly well. So this is a speed-up chart for, again, running up to 80 cores here. And we're writing codes with absolutely no granularity. There's no granularity control here at all, nothing manual. The system is managing parallelism using the heartbeat idea. And these are the self-speedups, okay? Speedups with respect to my one-count version. So incredibly good scalability, okay? So how do we actually compare to hand-optimized codes? Here we're comparing to hand-optimized codes. 25% slower than manually tuned codes. I was blown away by this. So you have a graduate student. Typically, my graduate students spend 1 day of their week to write an algorithm, 2 weeks to optimize it. Okay, that's the kind of effort, at least an order of magnitude. None of that happens anymore. You write your code, the system automatically gets you within 25% of the manually tuned code. It's incredible. Okay, so now, can we beat the manual? It turns out we can. Why? So here, we are comparing, this is the C implementation, the other one was ML implementation. This is the C implementation. We've compared our C implementation to OpenMP codes. And we are 50% faster than OpenMP codes optimized by others by using automatic parallelism management. Okay. How could this be happening? So we looked into it. How could this be happening? How could we be faster than manually optimized codes? Well, what's happening is that these optimizations are so tricky. Human beings do not do all of them. Okay? So what we noticed is that OpenMP codes do not actually optimize certain parts of their code because they think, oh, this is too tricky. I don't know how to reason about this, and so on and so forth. But our automatic system is able to extract all of that. Basically, our automatic system is able to extract parallelism from complex pieces of code automatically where human beings didn't dare to parallelize. That was the lesson. Okay, so conclusion. It's not only possible to bridge performance and safety by using high-level languages, declarative languages, we can even improve over human beings. I guess computer science has now gone into an area where we are starting to improve over human beings, and that's sort of aligned with that kind of trend. And how do we do that? I swear by these methods. So I love Turing theory. I love algorithms, complexity theory, graph, view of computation, analysis, and so on. And I also love church theory. I like the fact that you can actually formalize what you're talking about, mathematically reason about it. So, and this work combines both of these things. And also, I love building systems. I'm a bit of a hacker myself. So lots of engineering has gone into it. In this particular, I should say that in this particular work, a lot of the hacking was done by my students, not by myself. So perhaps the key lesson from this work is church theory and Turing theory together can bridge safety and performance. And we've only scratched the surface. Lots of interesting problems to work on and lots of improvements to do. Yep, so take your questions. Thank you for your attention.
Actually, I have a question for you. So far, all of the examples you've mentioned use like the fork join model. Have you thought about extending this work to like different paradigms, like futures, for example? Yeah.
A Popple paper, don't know what year, I think it's Popple 2024, where we showed that disentanglement extends to futures. Yeah, that's a very, very good question. So all of this work is fork join parallelism. It turns out disentanglement theory extends to futures. We haven't implemented it. That was just a theory paper. Yep.
Hi. A lot of the speedups that you measured for the heartbeat parallelism seemed to be measured looking at throughput. How does it affect latency?
So all of these benchmarks are, that's a very good question. So all of these benchmarks are not latency sensitive. None of them are latency sensitive. Now in another work with my graduate student, Stefan Muller, we have developed a different way of scheduling these computations, both for throughput and for latency. I don't think we considered the heartbeat at all. Let me think, just try to jog my mind a little bit. Yeah, that's a very good question. So I think it would work because the heartbeats that we're using here are like small enough, typically under a millisecond, that it shouldn't be a problem. But really research question, yeah. Excellent research question. Thank you. Yeah.
On one of your slides, you made a comment in passing. I'd like to ask you to elaborate on, if you would. You said that you need to move the parallelism up to the top of the graph. Yeah. And how, if you're using external libraries that you didn't write and they're using parallelism or not, is this advice about moving to the top of the graph actually usable in practice?
Yeah, 100%. So we are assuming there's some kind of primitive that says fork or parallelize here. So what the runtime system will do, typically in a situation like that, what our runtime system does is to keep this graph of tasks in the background. So you start executing A, and when you see an opportunity for parallelism, you mark it, but you don't realize it. You say, this is a parallelism opportunity. You go down, let's say that you see another par here. You mark that. You say, okay, here's a parallelism opportunity.
Mark it, the optimizer marks it.
No, the runtime system. Runtime system marks. Runtime system marks. By you, I mean the runtime system. The programmer just says, forward. Programmer is not aware of any of these things. But when the programmer typically says fork, their mental model is that there's a real fork. What this work does is that, oh, no, that fork is a virtual fork. You think of that as a virtual fork. A real fork happens only when a heartbeat comes in. And then the system decides which one of these, if I'm here, I have two forks that are available to me. Which one of these should I do? It turns out it's very important to do the top one. Why? Because there could be a huge computation here. You don't want to delay that. If you're lower, deeper in the computation, there's less likely to be more interesting things down there. Whereas here, if you delay this, you're delaying this entire thing. If you delay this, you're just delaying that little thing. That's intuitively what's going on. That turns out to be very important. Without that, the theorem doesn't go through.
So my question, I'm not sure if my question relates to your talk today, but I'm interested in parallel functional program for GPUs. So I'm wondering to what extent your ideas presented today carries over to parallel programming for GPU.
Programming is very, very different, as you know, right? Well, good question. I would hope that they generalize, but I have no evidence that they would, honestly. Yeah. So, I'm sorry, yeah. But we are working, I guess it suffices to say, one of my students and I are starting to work on GPUs and trying to basically realize these ideas in the GPU realm. We're hoping that it would work, yeah.
I apologize, it's a very vague and nebulous question, but I'll ask it nevertheless.
I love those questions.
Okay, so the one very high-level takeaway that I have from your talk, as a very much an outsider, is that if you really want to make, sort of really squeeze the juice out of parallelism, it has to happen in the runtime.
I would agree with that, yes.
Okay, so far, so you agree, right?
Yeah.
Now, okay, so let's just assume that on the one hand.
Yeah.
On the other hand, it sounds, and so, on the other hand, it sounds like if you do this stuff with C, and you have Guy Blalock and his buddies just really hand tweaking the C and doing really insanely cunning things there.
Yeah.
There, everything, it requires a lot of thought.
Yeah.
But everything, all the cleverness is being sort of statically encoded in the program syntax. The runtime itself is, I'm just saying, it's probably not doing a lot of sophistication. Is that an accurate statement?
That's accurate, 100%. Yeah.
Whereas in your situation, the program syntax is, the syntactic is like super simple, like sprinkle a little par here. And all the cleverness is going to happen in the dynamic world, right? And yet the C thing is actually sometimes better, right? Can you speculate on, do you think in the limit the dynamic thing is always going to be better than what you can encode in the program syntax? Or is it just that, well, if you are a genius, you could do it in the program syntax and you wouldn't need this insanely complicated runtime, but it's just really hard to figure out the exact incantations in the program syntax?
That's such a good question. So let me, where was this? Let me go back to this plot. I think this is very important too. So, Ranjit, as you know, C is, so a lot of this overhead, it turns out here, that's C, that's us, is due to just the fact that C code is assembly, right? Like, so as a human being, you can move register-based stuff around. You can reason about your memory allocation. You can reuse memory, right? So those types of things. Now, they are always going to be faster. I think there's no way to beat them. But they are always going to be unsafe. There's no way, in some sense, the faster they are, the more unsafe they are. And that's the problem, right? Because as you said, these guys have been spending their past 20 years writing these codes. Let's say that I'm a software engineer and I want to improve that piece of code. Oh my goodness, I would not even dare to change a single line of code because I'm probably going to introduce a bug. Right? So there must be some cost to safety. Like, if you want your car to be safe, you must have airbags. You can't say that I'm going to be, I'm going to be safe without airbags. You must pay a cost. And I think I believe we are at the fundamental, we are really close to the limit of that cost with these techniques. And why? These, comparison to these languages show that. I mean, this is an industry strength language, Go. Okay? This is a language that me and my graduate students developed in a research lab. We are 2x faster. Java, we are 2x faster. OCaml, we are 6x faster, while consuming less memory, at least 2x less memory. Right? So that shows you how effective these techniques could be. Yeah, I hope that I answered it. So I believe there's a cost to safety. It's not going to be free. And in some sense, these higher level languages show you, Go's and Java's and OCamls show you that even industry strength languages are paying a huge amount of this cost, but we are able to improve upon that. Yeah. Thank you. Yeah.
Like this far primitive that you introduced is not
Yeah.
technically free, right?
100% it's not free. Yeah.
Would you like comment like how much like overhead it has?
Oh yeah, sure. Yeah. I don't know if I have that's what this granularity control does basically, right? Yeah, I think this here. Oh, here are the overheads. Yeah. On average, geometric mean 10% over sequential code. Yeah. But without the granularity, without automatically granularity control, this can easily be 10x or 100x actually, depending on the code. Yeah. Okay. Thank you. Yeah.